So let us start. In this lecture, we will consider Bose and Fermi gases of elementary particles. Elementary particles. If you wish, you can write down very short title of the lecture. So it's a quantum ideal gas. So it's some kind of ideal gas which consists of quantum particles. So we consider a gas consisting of non-interacting, identical particles. We assume that the conditions are such that we can consider each particle as a massive point without any internal degrees of freedom. In the other words, each particle of the gas are just massive point, is just a massive point. Particles the last assumption is true for the gases of elementary particles. For example, gases of electrons, gases of protons, neutrons, and so on. This assumption can be also valid for gases consisting of atoms and so on, if the temperature is sufficiently small. The one particle, Hamiltonian, has a form. Here, this symbol stands for gradient, and the potential energy depends on the Cartesian coordinates, x, y, z. We assume that the gas stands in the box with the dimensions Lx, Ly, and Lz. So the box with gas looks like something this. The dimensions Lx, L sub y, and L z. The potential has the following form. It equals 0 inside the box. And infinity in all other cases. This model is now we have to find the stationary states of the system. I will not, this problem is well known in quantum mechanics, so I write down the solution. The wave functions, the stationary wave functions, so I ignore the dependence of wave function on time, read. And here, and x and y and nz are quantum numbers. They run all the integer numbers starting from 1. Please note that n cannot be set to 0. In this case, the argument of sinus equals to 0 and the sinus function equals to 0 too. I want to stress that each stationary state represents a superposition of waves. It's a superposition of states with different values of moment. For example, this function includes the states with the values of momenta p sub x equal. So okay, just x. Just okay. So okay, plus minus is not 1. Sub z equals this. Here we observe the main difference. Here we observe the first main difference between the classical gas and quantum gas. As we see, the momentum is quantized. Here I mean that the momentum takes discrete values, while in the classical theory, the momentum takes continuous values. Now we can write down the energies of the stationary states. So it's the energies of one particle states. They read. We can obtain this expression just by substituting the values of the momenta into the formula, to the classical formula. And we can just, if you want, you can verify that this is their energies of the stationary states just by solving a stationary Schrödinger equation with this Hamiltonian. So, okay. Let us change the whiteboard. Okay, this is not all. It's better to turn to the first module. Now, I forgot about one very important thing. The quantum theory tells us that each particle has its internal angular momentum, which is called spin. The quantum states of one and the same particle are distinguished. The quantum states of one and the same particle with the fixed values of quantum number and x and y and z are distinguished by the value of the projection of the spin angular momentum on the fixed axis. If the particle have a spin s, the projection of spin takes values minus s plus 1, etc., up to the total number of possible values of spin projector is denoted by G sub s, which is equal to s plus 1. And so-called spin degeneracy. As we see, now we see that each state of the quantum particle is determined by the numbers n and s and sigma. The states which are determined by these numbers are one particle microstates. Now we are going to construct a statistical mechanics of the system of quantum particles. And now we are going to another board. At the previous lecture, we have obtained an expression for the grand thermodynamic potential of the system of identical particles. Which equals, no, it's not plus minus. No, yes, it's plus minus theta. And here is the sum runs over all quantum numbers. All quantum numbers. Right, okay. Let's say all one particle states. All one particle states here. Logarithm. That's mu minus E sub L over theta. Here, the index L just labels one particle states. The top sign, here plus and here minus, stands for bosons. It's the particles with integer spin. The downside stands for fermions. It's the particles with half integers. So on. In the case at hand, one particle states are labeled by the quantum numbers n, x, and y, and nz, which run integers, and spin projection, which take 2s plus 1 different values. And the energy of a state defined by this formula. In this case, we obtain the following expression for the grand thermodynamic potential. Okay. We can simplify this expression by taking a sum over sigma. The expression in the sum does not depend on sigma, so we have 2s plus 1 identical terms here. So we get here we get GS, because from here we get 2s plus 1, and here we have a sum over n. first formula represents an exact expression for the grand thermodynamic potential of the gas of identical particles with spin s. This expression is not convenient for us. Okay. And here I want. I'm too fast. And here I want to attract your attention to the second difference between the quantum gas and classical gas. The expression for grand thermodynamic expansion accounts the statistics of the particle. And depending on the nature of point of particles, we get the system of bosons or the system of fermions. And they have different thermodynamical properties. So the quantum gas is different from classical gas in two respects. The moment is quantized, and the statistics is taken into account. Now we are going to study the expression for the grand thermodynamical potential of the quantum gas. We are going to understand the properties of the gas. When we look at this formula, the first difficulty is that we have a summation here. We have a summation over one particle states. It's not easy to compute the sum. And our first simplification will be switching from summation over n to integration. When we replace summation by integration, we say that the momentum of the particle changes continuously. This assumption generally true. Please note that in the thermodynamics, we consider very big systems, very big in size, in space size systems. So the numbers L sub x, L sub y, and L sub z, in fact, they are very big. And the momentum changes, for very big systems, the momentum changes quasi-continuously. From the physical viewpoint, This redefinition means that we ignore quantization of translational motion, but we still take into account the statistics of the particle. In fact, this step can be done almost in all cases. The only case when the quantization of translational motion is important in our course is the Bose condensation. It appears in Bose gases at very low temperatures. So we are making first simplification. Okay, 1 second. Okay, so now the quantum numbers change continuously. Our second step of simplifications is to replace integration by quantum numbers by the integration by a momentum. So we introduce a new formal variable which has a sense of the particle momenta by the rule P. Okay. Look at the formula. Okay. And so X and sub Y and sub Z. And here the variables py, px, py, and pz run over the set or run over non-negative numbers. And the volume element transforms as follows. Okay. Yeah. Lx, Ly, Lz divided by Q, H bar Q. Dx, dpy, dpz. And here we have a product of dimensions of our volume of our body in which gas is contained, and here it's a volume of gas. So we can write okay. Now represent as the integral over moment. Okay. So okay, just let me erase better my whiteboard. So omega equals plus minus gs theta, and here v divided by b cube and bar cube integral d sub x dp sub y and integral dp sub theta. And here the logarithm 1 minus plus e p squared to m theta. Okay. Please note that all moment projections run over non-negative numbers. In the moment space, the area of integration is given by the octant with all the positive values of p. So if we have x, y, z, and here the volume that corresponds to the area of integration. We can make the integration limits infinite. Because here this expression depends on the moment squared moment. So, and here I do the following: I put infinite limits here, and once each such step doubles the value of integral, I put here 8. And now I can join all these guys into the cube. 2 multiplied by p and multiplied by h bar. So, okay, we have such integral, and now this expression is still complicated. We are going to simplify it. We see that the function under the integral depends on p squared. Just it's p sub x plus py plus pz squared. So it depends on the radial coordinate in the space of moment. In this case, it's convenient to introduce spherical coordinates in momentum space. So we put P sub x equals to P sin theta. You can put, okay, tilde above, just to be not confused, these thetas are different. Cos phi, P, y, P, sin phi, and P sub z plus P multiplied by cos. The variables theta, tilde, and phi have a clear geometric meaning. If the vector P denotes the current value of momentum, the angle theta tilde is the angle between z-axis and the vector of momentum, and angle phi obtained as following. We project the current value of momentum on the plane x sub y. Okay. And measure an angle between the projection of momentum onto the xy plane and x-axis. The variable p is just a length of vector. So p is a non-negative number. Theta changes between 0 and pi, and phi between 0 and 2 pi. The volume element transforms as follows. Here, tilde. Okay. This is the standard formulas which I do not write out and prove here. And now, okay, we have the expression for the grand thermodynamical potential. Oh, no, it's not correct. 0 to 2 pi d phi, 0 to pi theta d theta, and from 0 to infinity over 1 is e squared divided by 2 m theta. The integral in the angular variables is easily computed. Yeah. 2 over 2 pi. And here, so I just rewrite. This one, hit, let's close. Just. I replace these two integrals by 4 pi. Okay. It's almost end, but not the end. The problem here is that, okay, no, it's very simple integral. It needs this integral cannot be computed in elementary functions. So we need to bring it to a more or less standard form. The best way to do this is to introduce dimensionless integration variable. Please note that the momentum has a dimension. We put P equals to m theta x. It's the same that x equals p squared over 2 theta. The meaning of the variable x, please note, it's not a coordinate, is simple. It's a ratio of particle energy, of current particle energy to the energetic temperature. And if we compute differential, dp, we will obtain, no, not 2m, m theta by 2x d. Okay. Okay. So and now we get omega plus minus gs theta 4 pi. Now we change the measure of integration and change the momentum. So we get 2m theta to the power 3/2. And in the bottom, we'll get 1/2 from here. Okay. And now we have integral. The limits are the same. X runs from 0 to infinity. And here we have logarithm 1 minus cos e divided by theta minus x to the power 1/2 dx. So should we make a break right now? Okay, so if we proceed without break, let's continue. Now we are going to consider this integral. It has a quite complicated form because we have a logarithm and exponent inside of it. We can simplify it. Let us apply okay, it's not necessary for me. Let us apply the formula of integration by parts. U dv equals to uv minus integrals v du. And let us take by the logarithm by the function u. And the remaining part by dv. V equals x to the power 1/2 the x. Well, it's the same, it's 2/3 of x. No. It's differential of 2/3 of x to the power of 3/2. So we have integral minus okay. And okay, we have here, and we integrate by parts. So we have 2/3 x to the power 3/2, and here logarithm. We should estimate the logarithm in the limits 0 and infinity. And here we have a contribution of integral contribution. So we had to differentiate the logarithm by x. So when we differentiate, we get minus from here. So we have plus integral 0 to infinity. And here, 2/3 x to the power 3/2. And now I differentiate. I use the rule of differentiation of composition. When I differentiate logarithm, I get a fraction. Here, the denominator. And now I have to take a derivative of exponent. And here, and the derivative of exponent is minus plus e to the power. Okay, now I simplify, and here dx. Now I'm simplifying this expression. I take minus plus here, and I divide the fraction, both parts of fraction, by the exponent. So when I divide by this exponent here, I get 1. And here, I get exponent with reversed, with opposite degree. Okay, x minus mu divided by theta minus plus 1. Now we can consider this term, which doesn't include integral. I state that it is equals to 0. When x is set to 0, we have 0 because x equals 0. When x goes to infinity, the exponent becomes a very small number. In this case, I can use the Taylor series expansion for the exponent, right? Something like this. And in the limit of big X, this contribution grows, and exponent decreases. The exponent decreases much faster than X grows. So we have 0. The final expression for the grand thermodynamic potential.
Извините, Дмитрий Сергеевич, а можете писать крупнее, пожалуйста? Ничего не видно.
Okay, I will write a little bit bigger. And now I can write the final form of grand thermodynamical expansion potential for the ideal quantum gas. Here I get minus because here plus minus and here plus minus. They give minus. Here 2 and this 2 here 2 eliminate each other. And I write down here from here I take 3 and I write down the remaining part. 4 pi gs 2 and theta. Okay, I will try to write a little bit bigger. I forgot about your question. Okay. And here I have an integral from 0 to infinity, x to the power 3/2 dx, and here exponent x minus mu divided by theta minus plus 1. Okay, and here I put a point. This is the final expression for the grand thermodynamic potential of the quantum gas. By construction, the grand thermodynamic potential contains all the valuable information about the thermodynamics of this gas. Our problem, the problem is that the integral here can be expressed in terms of elementary functions, and we can't compute it explicitly. So we have to study. This gas without maybe in some implicit form, right? And the first step of our computations, we verify that the system has a correct classical limit. Yeah, I take position here. Classical limit. Okay. Classical limit. As we have already discussed, we have a class in the classical limit, the occupation numbers are very small. In this case, the chemical potential is a big negative number. Okay. The ratio of chemical potential to the temperature is big negative number. And in this case, the exponent here is very big. And we can ignore 1 in comparison to exponent. So we have a classical. This means classical grand thermodynamic expansion in the following form. Okay, for pi gs 2m theta to the power 3/2 2 pi h bar to the third power. And here I have integral to the infinity exponent to the minus x. Oh, no, it's not correct. Here I write out the integral exponent here, and here I write f integral over minus x to the power 3/2 dx. I will not compute this integral. It's not difficult, and I allow the computational details up to you. I just want to say a couple of hints how to find its value. At first, we can make substitution. X equals t squared. Then we make substitution x equal to t squared. And then we change integration limits from 0 to infinity to the infinite integration limits. And then we integrate by parts and use Gaussian integral minus t squared dt equals half of square of pi. So the details of the computations is up to you. I write out only the value of this integral. Please note that it's a constant. Now we can substitute this expression and obtain the result. Gs 2m theta 3/2 square of pi 3 here. 2 pi. Okay, it's too small. My font is too small. Here, half. So here, 4. And here, somewhere here, I forgot volume. Please note, I forgot volume. Here. Here, I should have volume. Now, we can make simplifications. We just you annihilate this force and this thirds. And here we have pi and square of pi. They give pi with the degree 3/2. Here we have the degree 3/2, so we can join them together. Just 2m pi theta over 3/2. And now I'm erasing all the things, and here minus. And this is the expression for the classical ground thermodynamical potential of the quantum gas. Please note that the Boltzmann gas, which is associated to the quantum, to the classical, gas corresponds to the spinless particle. So Gs equals to 1 and S to 0. So you can say that this is a spinless particle. Or some kind of, or maybe scalar particle. You can compare obtained expression with the previously with the corresponding formulas of previous lectures, and conclude that it's indeed the ground thermodynamic potential of the classical gas. Okay, we see that we are correct in the classical limit. Let's jump to the quantum story. We may be interested in the thermodynamic functions of gas. Here, I will focus on a limited number of thermodynamic functions, namely pressure, entropy, the number of particles, and internal energy. Let us first compute the average number of particles in the system. We have, from thermodynamics, we have that the particle number equals to the gradient of, to the derivative of ground thermodynamic potential by the chemical potential for constant theta and volume. And we can compute this derivative, it's not difficult. Please note that all this coefficient is a constant, it doesn't depend on mu, so we should not differentiate it. We should the chemical potential involved only in this integral. So we can differentiate integral. We can make this by transposing differentiation and summation. So, okay, minus minus gives plus. And now I differentiate integral. So I have to differentiate exponent, and I obtain x to the power 3/2 exponent. Okay, I forgot. Okay, please, I made a mistake. Here I forgot here theta, and here theta, and theta is here, and here theta. Okay. So, okay, here theta v. Now I differentiate. I differentiate function. The derivative of function is the derivative of square, just minus mu divided by theta minus plus 1. And here I take the derivative of it squared, the derivative of function, because derivative of function minus 1, here minus, so they annihilate each other. Here I get divided by theta, and here theta appears here. And they give 1 of these thetas. And here dx. Again, the problem is that the expression looks very complicated and so on. Our idea is to simplify this integral by integration by parts. Okay. I take all this expression here by the differential of function dv, and I take here by the function u. So I get x to the power 3/2 exponent x minus mu divided by theta, and here exponent x, okay, minus mu divided by theta minus plus 1 squared dx equals. Okay, what I should do? This guy is a total derivative of something like this. Exponent, okay, let's write bigger. Exponent x minus mu divided by theta minus plus 1. And here, because we have a minus, so we have minus sign. And here, x to the power 3/2. And we should estimate if the limits 0 and infinity. I say that this guy equals 0. When x sets x equals 0, we have 0. When x is very big, we have very big exponent. Something divided by very big exponent equals to 0. And now we are going to look the integral term. So we have plus because of this minus integral over the limit plus 0 x 3/2. Okay, x 1/2 because we differentiated x to the power 3/2. Here 3/2, and here x minus 0 divided by theta minus plus 1. Okay, and this expression looks much better than the previous one. So we can compute, we can write out the total the average number of particles in the gas. So 3/2 and 1/3 give 1/2. So we have 2 pi gs qm theta to the power 3/2 v 2 pi h. Oh, okay, let me write bigger. 2 pi h bar to the third power. And here integral, and here x 1/2. Okay, dx. That's fine. X minus mu divided by theta minus plus 1. This formula is very important to us because it connects the particle number and chemical potential. In applications, we prefer to express thermodynamic functions of the gas in terms of particle number. The chemical potential is less convenient quantity. So, if we are able to solve this equation with respect to mu, we will find chemical potential as a function of total number of particles, volume, and temperature. Another important quantity is the gas entropy. To obtain it, we should differentiate by the temperature. And now, let me take the differentiation. Please look at the expression here. Here we have temperature in two places, here and here. So we should use Leibniz rule. When the derivative bite over the first multiplier, we get minus 5/3, because here the degree 5 divided 5 seconds, and okay, 5 seconds, okay, 5/6. Okay, it's better to write two different 1/3, 5 seconds, and here for P, GS 2m theta to this power 3/2 v. And here we divide 2ph bar to the third power. And here we get integral from 0 x to the power 3/2 dx. Minus plus 1. It's the first contribution. The second contribution has similar structure. Similar structure is here because we differentiate integral. So we have 1/3 4 pi gs 2m theta 3/2. When we differentiate by temperature, we get temperature to the second power in the denominator. It annihilates one temperature here, this one. So I write temperature here, 2 pi h bar to the third power. And here I get the integral x to the third power, exponent x minus mu divided by theta. Okay, I should remember the sign. I think here the sign minus. And here the exponent minus plus 1 to the second power dx. We can make similar simplifications in here. And I suggest for you to make these simplifications, but while I prefer to write down the result. Okay. Oh, okay, so as minus, so it's here plus. I forgot, here should be plus. So I write 4 pi gs 2m theta to the power 3/2 v 2 pi h to the cube. And here I collect this integral and this integral from 0 to plus infinity. Here 5/6 of x minus mu divided by theta. X to the power 1/2 dx. And here exponent x minus mu divided by theta minus plus 1. Again, we have not so good expression, which is quite complicated and so on. But we can find the internal energy of the gas quite easy. We use the relation between the internal energy, grand thermodynamic expansion, and entropy and chemical potential. I have quite little of time remaining, and I suggest for you to substitute these expressions here and obtain the result. And I state that I will obtain 1/2 1/2 for GS 4 pi to m theta over 3/2 theta v divided by 2 pi h bar to the third power. Minus, okay, it's too small, okay. And this expression very similar to the grand thermodynamic expansion. It's the same expression modulo the factor 3/2. Minus over the factor minus 3/2 of omega. In the other words, we have a very important formula, which is now very simple. Omega equals to the minus 2/3 of u. Please take this formula in frame. It's very important formula. Another important formula follows if we combine this one and the expression for the thermodynamical, grand thermodynamic potential in terms of volume and pressure. If we take these two formulas, we will find that PV equals to the 2/3 of u. And in other words, okay, and in other words, and from here we can express the pressure. Pressure equals to 2/3 of u divided by v. That is, that means that the pressure is determined by the internal energy density. Let me mention that this relations follows from the very simple fact: the energy is a quadratic function of momentum. If we had a linear dependence between momentum and energy, for example, in photons, we will get this. And this expression is known now for us in the thermodynamics. We obtained it in the thermodynamics of radiation. Can we obtain something interesting else? Yes. And I suggest to consider an adiabatic process. Adiabatic process. Adiabatic process is a thermodynamic process in which our system is not in heat contact with surroundings. That means that entropy is constant. The curve of adiabatic process is determined by the equation du minus pdv. It's just first law of thermodynamics. This first law of thermodynamics for adiabatic process. We don't have the system doesn't get heat, so we get this one. And now we see that the internal energy is expressed in terms of pressure and volume. So we get something like this, 3/2 d. So we have d of 3/2 PV minus P dV. And now I differentiate and collect all in the left-hand side. So I get 5/2 P dV plus 3/2 V dP. To simplify, I can divide, okay, P dV. Okay, I can divide the left and right hand side by 3/2. So I write here, and I multiply the left and right hand side by the volume to the power of 2/3. And I get differential of P V to the powers 2/3 equals constant, equals to 0. Integrating, we find the equation of adiabate. It's some, okay. It's the equation of adiabate. In case of classical ideal gas, we had the same, in case of classical ideal gas, we had the same equation of adiabate. So the curves of adiabatic process in case of classical ideal gas and quantum ideal gas have one and the same form. The only important difference that in quantum case 5/3 is not a fraction of heat capacities Cp and Cv, because Cp and Cv are not constant in quantum case. So the time of the lecture is over. If you have questions, you can ask me.
То есть это такое выражение для адиабаты, но в квантовом случае у нас Пейцевы не являются константами просто.
As a question, is it the equation of adiabate? But yes, it's true. The difference of classical and quantum case is the following. In classical case, the power of adiabate, classical case, we have something like this, and this gamma is the Okay, the degree of polytrope, and gamma equals to the fraction Cp and Cv. It's a classical case. In quantum case, we have the same expression, we have the same equation of curve, we have the same value of gamma, but gamma now is not a ratio of heat capacities, because heat capacities Cp and Cv depend on temperature. We will compute them on the next lecture. Okay, any other questions? Okay, no questions. Thank you for the lecture. We will meet on Friday at 10:35. See you on Friday.